Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. This module will learn the details about virtual memory. So, the learning objectives for this module are to understand what is meant by virtual memory, to understand what is demand paging and what are meant by page faults and what happens, how the system handles page faults and how the performance of demand paging is found. So, we learnt in memory management that any process that needs to be executed has to be placed in the main memory or in the physical memory, or the currently executing instructions should be present in the physical memory. And what we can do is that we can place the entire logical address or the entire process in the physical memory. That is what we had been doing in the earlier memory management schemes, whatever we have learnt earlier. Even though in paging or in segmentation or in page segmentation, we try to put in the whole process into the physical memory at a particular time. But the problem here is that it will limit the size of the program to the size of the physical memory. The size of the program cannot become larger than the size of the physical memory. So, in the case of virtual memory technique, we try not to place the entire program into the physical memory, and the support for this comes from, say you have some code which are handling error conditions. Such a code may not be executed always, and very similarly when you have some space that is occupied by arrays, tables, etc., the entire array space may not be occupied. You may have declared the array for some say 100 locations, but the space occupied can be maybe only 10. The remaining locations may not be used at all. And very similarly, you can have some features of the program which may not be used at all. And in that case, the code which is needed for these features need not be brought into the physical memory, need not be used at all. So, when the entire program, even when the entire program will be used, at a particular time only certain portions of the program will be used. Not all portions, not all the instructions will be executed at a particular time. Only one instruction is executed at a time, and you may use the data corresponding to that instruction at that particular time. The remaining instructions are not used at all at that particular time. So, even if the whole program is usable, the entire program will not be used simultaneously at a particular time, and all these contribute to the support of having virtual memory. So, now the programs need not be constrained by the physical memory which is available, okay, and more physical memory space is now available for more programs. So, if you bring in or if you keep in the instructions which are needed only now, then the remaining space is free for other programs instructions. So, what is virtual memory? Virtual memory separates the user's logical memory from the physical memory, and in this case only part of a program needs to be present in the physical memory for execution, and because of that the logical address space can be much larger than the physical address space. So, this allows a large virtual memory to be available for programmers when only small physical memory is available. So, just look at this diagram. Here you say that the virtual memory has got pages from 0 to n. There are n plus 1 pages here, and you have some memory mapping scheme, and you have the physical memory. Generally, you try to put all these pages from 0 to n into the physical memory, but now you do not put all the pages into the physical memory. Only the pages which are currently needed will be put in the physical memory. The remaining pages can be placed in the backing store or in the disk. So, now the virtual memory can be much larger than the actual physical memory available. Say if there are n plus 1 pages here, and say if there are only n by 2 number of pages space in the physical memory, even then it is okay, because you use only a few pages in the physical memory. You keep only a few pages in the physical memory. Remaining pages are kept in the backing store. So, because of this virtual memory, you allow address spaces to be shared by several processes, and because of this you can create efficient processes. And how do you implement virtual memory? It can be implemented by demand paging as well as by demand segmentation. So, demand paging. What is demand paging? It is a paging system in which you combine swapping also. So, here in demand paging, the processes actually reside in the secondary memory. Secondary memory, it can be the disk. And whenever the process needs to be executed, only then the process is brought into the main memory. Else it is not brought into the main memory, it is kept in the secondary device only. And hence what we do here is that instead of bringing the whole process, only the pages which are currently needed are brought into the main memory. So, in this diagram, say you have some few space that is allocated for program A and some physical frames that are allocated for program B, and you keep all these information are kept also in the secondary storage device. So, when you need to bring in program B from the secondary storage device, you can, and if you need space here, you can move out or swap out this program into the secondary storage device and bring in the required number of pages for program B into the main memory. So, you can swap in and swap out programs so that you get space for programs to execute. So, what is demand paging? In demand paging, you avoid bringing in pages which will not be used at all. So, I told you about some error routines which may not be used, or some feature of the program which will not be used at all. If you have such a kind of features that are present in the program, then you do not bring those pages into the main memory at all in the case of demand paging. So, because of this you need less I/O. Why less I/O? Because you need to access from the disk, bring from the disk into the main memory and then move back to the disk. That will be reduced because you will not bring anything which will not be useful at all. And the next advantage is that you will need less physical memory space, and it is faster response is possible because you can bring in the programs of many users into the physical memory at a particular time. You have more space in the physical memory and hence a faster response time to the users, and more number of users programs can be accommodated. So, now to differentiate between the pages which are in the main memory and those on the disk, some additional mechanism is added to the page table. So, as I told you, in demand paging, you do not have all the pages kept in the physical memory at the same time. Only the pages which are currently needed are brought into the physical memory. So, how do we identify this? How do we know which page is in the main memory and which is in the backing store? We have a bit called the valid invalid bit. So, this bit, if it is set, then it means that it is valid. Valid means that the page is a valid page and also it is present in the main memory. But if the bit is set as invalid, then it means that either the page is not valid, or it can even be the case that the page is valid but it is not present in the main memory. So, this valid invalid bit is useful when you do the address translation for a particular process. So, just look at this example. You have the logical memory where you have 8 pages A, B, C, D, E, F, G, H, and A, B, C, D, E, F are actually the valid pages, G and H are not valid pages, and they are present in the backing store. And of these 6 pages, only 3 pages are kept in the physical memory. The remaining you have only in the backing store. So, now look at the page table. Page number 0 corresponds to page A. Page A is present in the physical memory, and hence you update the page table as valid, and the corresponding frame number is also put into the page table. But page B is a valid page, but it is kept only in the backing store. It is not kept in the physical memory now, hence it is marked as invalid. The third page C is in the backing store, it is also in the physical memory, and hence it is marked as valid, and the frame number 6 is put here. And the next page D, it is kept in the backing store, it is not in the physical memory, and hence it is marked as invalid. So, this is how the valid invalid bit will be set when you are having demand paging mechanism. So, now when the process accesses the pages that are present in the main memory, then it will proceed as normal. So, in the earlier case, page A was present in the main memory. So, if there is an access to that page, then it will proceed as normal. But when you are trying to access a page which is not in the main memory, then a trap is given to the operating system, and this is called a page fault. That is, say for example, in the earlier example we saw that page B is kept only in the backing store, it is not present in the main memory. So, when you try to access that particular page, you find that the page is not in the main memory. You find that the valid bit is set, is not set, it is invalid, and hence a page fault is given to the operating system. So, this page fault may not be due to an invalid address error. It may be it may be the result because of the OS failure to bring the desired page into the main memory. So, how do we handle this page fault? For that, you have another internal table which is kept mostly in the process control block to decide whether this invalid reference means that it is actually an invalid page or it is a valid page but not brought into the main memory. So, when you look into the page table, you understand that whether the valid bit or the invalid bit is set. If the invalid bit is set, you understand that there is a page fault, but the invalid bit can be because of 2 reasons. Either the page itself is an invalid page, or it is a valid page but kept in the backing store or in the disk. So, you look into this internal table in the process control block and decide what to do about it. It is even after looking into this internal table, even after that, if you find that it is actually an invalid page, then the process is terminated because it is trying to access some illegal memory location. But if it is a valid page, but the page fault is generated just because it is not in the main memory, then you try and handle this page fault. So, how do you handle the page fault? You get an empty frame from the free frame list. Empty frame in the physical memory is found out from the free frame list, and you bring that page in the backing store into this free frame in the physical memory, and you reset the internal table in the process control block, and you also reset the page table and mark the valid bit as 1, and then you need to restart the instruction. So, the instruction is restarted. When the instruction is restarted, you find that the page is now present in the physical memory and the execution of that particular instruction is carried out. So, if you look at the steps that are involved in handling a page fault, say now there is an instruction called load M, and corresponding to this instruction you try to look into the page table and a CPU will generate a logical address. So, you look into the page table to find out the corresponding physical address, but you find that it is marked as invalid. So, if it is marked as invalid, a trap is given to the operating system. The operating system now finds that it is marked invalid because it is kept in the backing store. So, once it understands that, it tries to get this page from the backing store and brings the missing page into the physical memory, and it will find a free frame here and bring it to the physical memory, and then it will reset the page table, say that this is a valid one, and then the instruction will be restarted. So, when a page fault occurs, you see that the process is interrupted, and when the process is interrupted, the state of the process is saved. So, after handling the page fault, the process is restarted in exactly the same place and stage as where it left earlier. And you can start executing a process even with there is no page in memory. So, when you start executing a process, it is possible that you do not even have to allocate a single page space in the physical memory for that process. You can just start the instruction, and the first instruction will itself will result in a page fault, and then you can bring in the required page into the physical memory, and then you can continue from there. So, when all the needed pages are brought into the physical memory, there will be no more page fault, and this is called pure demand paging. That is, you never bring a process into the main memory until it is required. Even a single page of the process is not brought into the main memory until it is required. So, how is this carried out? This is because of this property of the programs called locality of reference. That is, programs tend to have a locality of reference. That is, say you are executing a particular function, all the instructions generated mostly will be within that particular function only. It will not be an instruction that will be referring to some other function. Mostly it will be inside that particular function. So, a process will be executing in one particular locality at a particular time, and then after some time they move on to another locality and execute in that locality, and so on. So, when a process is executing in one particular locality, the pages corresponding to that locality alone need to be brought into the main memory, and then you will not have much of page faults. You will have only less page faults if all the pages of that locality are brought into the main memory. So, this will give a reasonable performance for demand paging. But now what happens if there is no free frame? I told you, when you are bringing a process into the main memory, when you are bringing a page into the main memory, you try to find out if there is any free frame in the main memory. But what will happen if there is no free frame in the main memory? Then in that case, you need to find some victim frame in the main memory. I swap that page out into the secondary storage device, and then you swap in whatever you are bringing from the second storage device into this particular place. So, now when there are many frames in the main memory, which one do you choose to swap out? There are different algorithms for that, which are called the page replacement algorithms. We will learn about these page replacement algorithms in the next module. So, you can analyze and find out which algorithm will result in the minimum number of page faults, and use that particular algorithm to find out or to select the page for replacement. And it is possible that some page may be brought into memory several times. So, when you are swapping out pages and when you are swapping in pages, you may bring some pages into the memory several times. You would have swapped out and then bring in, and so on. So, when you are learning about the performance of demand paging, we need to understand about this effective access time. The effective access time when there is no page fault is same as the memory access time. That is, you try to access a particular instruction in the physical memory, and that page is present in the physical memory, and the memory access time is the effective access time. But if a page fault occurs, then you need to read the relevant page from the disk, and only then you can access the memory to access the desired word. So, if P is the probability of page fault, and P can take values between 0 and 1. And if P is 0, if the probability of a page fault is 0, then it means that there is no page fault at all. If P equals 1, if the probability of the page fault is 1, then every reference is a page fault. So, the effective access time is defined as 1 minus P into memory access time plus P into the time required for the page fault overhead. So, here we can see that the time that is involved in this page fault overhead is very large. We saw a sequence of steps that are involved in this page fault handling. So, once a page fault occurs, you need to handle the page fault, which takes a lot of time, which includes disk I/O, swapping page out, swapping page in, restarting, etc. and so on. There are a lot of overhead in that. So, I will just give you a list of the sequence that will happen when you are servicing a page fault, basically to understand how much amount of time it will take to service a page fault. So, when a page fault occurs, you trap to the operating system, and when a trap is given to the operating system for the current process, you need to save the user register values, and you need to save the state of the process of the currently running process, and all these have to be done. And then you need to understand, you need to find out whether the interrupt actually was a page fault, or you need to find out what kind of interrupt it is, and you need to understand that it is that of a page fault. And then you need to check that the page reference was legal, and then determine the location of the page on the disk. So, if it is a page fault, you need to find out whether it was a valid page and find the location of that page on the disk. And then you need to read from the disk to a free frame. Now, this reading from the disk takes some amount of time. Disk I/O is slow. So, you have to wait in a queue for the disk until you are serviced for this reading from the disk. And once you get the disk, you need to issue a read from the disk into a free frame. So, you need to wait in the queue for the disk until your request is serviced. Then you need to wait for the disk device seek and latency time. What is device seek and latency? The disk head should be moved to be placed on the appropriate location from where it is read from the disk. That will take some time. And then you need to look at the transfer time, the time required to transfer the page from the disk into the physical memory. So, you begin the transfer of the page to a free frame. And now we can see that this process is waiting, it is not utilizing the CPU's time, and it is waiting till this disk I/O is getting over. So, in the meantime, the CPU can be allocated to another process. So, some CPU scheduling mechanism could have been used, can be used, and another process can be given the CPU. And once this disk I/O gets over, the transferring from the disk to the main memory gets over, you get an interrupt from the disk saying that I/O is completed. And when the interrupt is come, the interrupt has to be serviced. So, the currently executing process register should be saved, the state of the currently executing process should be saved, and then you need to understand that what kind of interrupt it is. You understand that it is from a disk, you understand it is an I/O operation that has got over, and once you have understood that the disk I/O is completed, you need to correct the page table and the other tables to show that the desired page is now in memory. So, the internal table, the page table you mark as valid, and you do all changes. So, that will be part of the interrupt service routine that will be executed. And once all this is done, this process now will be put into the ready queue, and it will be waiting for the CPU to be allocated again. So, after the CPU is allocated, then you need to restore the user register values, the process state, the new page table should be loaded, and then you need to start the interrupted instruction. So, here you see that whenever a page fault occurs, it takes a long time to service the page fault. So, this servicing the page fault takes some amount of time, and if the probability of this page fault is very high, then it means that it will affect the effective memory access time. So, suppose if you have a page fault service time as 25 milliseconds and one memory access time is 100 nanoseconds, and the effective memory access time now becomes 1 minus p into 100 plus 25 0 into p. So, you find that the value depends on the value of p. So, if value of p is, even if value of p is 1 by 1000, you have 24,999 nanoseconds as the effective memory access time. But if you do not have a page fault, then you have, if the page fault is 0, page fault rate is 0, if p is 0, then you have only 100 nanoseconds as the effective memory access time. Hence, this page fault rate should be reduced as much as possible for the effective access time to be better. So, the effective access time is directly proportional to the page fault rate, and hence the page fault rate should be reduced. So, now just look at this problem. We will see how the effective access time is calculated. You have a demand paging system with a paging disk and the average access and transfer time of 20 milliseconds. So, the address are translated through a page table, and the access time of 1 microsecond for one memory access is given. And each memory reference through the page table takes 2 memory accesses. So, once you need to look into the page table, get the entry from the page table and then look into the physical memory to get the actual memory access. So, 1 microsecond for one memory access, you will need 2 microseconds if you are using the page table. And to improve this time, they have used an associative memory, and that will reduce the access time to only one memory reference. You do not have to look at the page table from the main memory. The entries of the page table will be kept in an associative memory, and you can look into the associative memory, get the entry, and then just look into the main memory to get the exact memory location. So, 80% of the accesses are in the associative memory, and of the remaining 20%, 10% causes page faults. So, 10% of 20% is 2%. So, 2% of the total causes page faults. Now, we need to calculate the effective memory access time. So, here it is given that 80% of the accesses are in associative memory. So, 80% will need only 1 microsecond, and you have 18%, the remaining 20%, of the remaining 20%, 2% has got page faults. So, remaining 18%, you can't find the page table entry in the associative memory, it will be present in the main memory. So, you pick up from the main memory the page table entry and then try to access the memory location, physical memory location. So, 2 memory accesses, 2 microseconds for that. And for the 2%, when you get a page fault, you need to access the paging disk. You need to bring the page from the disk into the physical memory. That takes 20 milliseconds of time. So, the disk transfer time is 20 milliseconds. So, along with this 2 microseconds, you also need to add 20 milliseconds, which is 20,002 microseconds. So, for 2% of the time, you need 20,002 microseconds. So, the effective memory access time goes as, so for 80%, for 80 by 100 it is 1, for remaining 18 by 100 it is 2, and for 2 by 100 it is 20,002. So, it comes to around 401.2 microseconds. So, here you see that even though you have 2%, only 2% of page faults, you find that the effective memory access time goes to 401.2 microseconds compared to this 1 microsecond if you find the page table entry in the associative memory. So, the effective access time is directly proportional to the page fault rate. So, page fault rate have to be reduced as much as possible. So, summarizing what you have learnt in this module, we learned what is meant by virtual memory. So, it is possible to have a logical address space which is much larger than the size of the physical memory, and that is called virtual memory. And then we learned what demand paging is, that is, a page is brought into the memory only on demand, only when the page is needed, it is brought into the physical memory. And whenever the page needed is not present in the physical memory, a page fault is generated, a trap is given to the operating system. The page fault is serviced by the operating system and the required page is brought into the physical memory and then the instruction is restarted. So, the effective memory access time we saw how to calculate effective memory access time, and we found that the effective memory access time is directly proportional to the page fault rate. References, acknowledgement. Thank you.